All right, welcome back to pre-calculus. We are going to continue our lessons on complex numbers, polar forms of complex numbers. Okay, so let's go ahead and share the screen, and that way we can just kind of get started with it. Okay. Alrighty, let's get it away. And we will get started with this and with this. Yeah, I don't know what that is. Oh, go figure. All right, here we are. Nope, I don't want any of this. I want this thing. Okay, sorry about that. All right, so it's a pretty gentle introduction about how to graph numbers on the complex plane. Okay, all they want us to do is to plot these points. I'm more than confident that you guys can go through and do some of this. Okay, 1 plus 2i. Okay, it's the same kind of graphing you've done a million times before, so just realize that the x-axis is the real axis and the y-axis is the imaginary. That's pretty much what we do. Again, positive parts over here, negative parts over there, positive imaginaries up, negative imaginaries down. Okay, so I'm not going to worry too much about you guys being able to graph these things, okay? But that's how it works. All right. We're talking about the modulus. They're talking about the length, the distance, okay? So if we have a 3 plus 4i, okay, yeah, there we go. We have a 3 plus 4i. What that means, 1, 2, 3, 1, 2, 3, 4. They want to know what this is, okay? So the sides of it, this is the sides of a triangle, right? We have a size of 3, a length of 4 here. So 3 squared plus 4 squared is equal to 25. The modulus r, that is equal to 20, the square root of 25, so 5. Okay, so Pythagoreans Theorem, same thing you have been doing the entire semester. Okay, so again, nothing really to fear here. Should be able just to kind of run through that and check. Okay, this one's negative 11 plus 60i. I don't really want to graph that because it's going to be a bit longer, but negative 11 plus 60i, so we're going to have the square root, negative 11 squared plus 60 squared. Okay, so bring up our calculator. So we've got 11 squared is 121. So we have 121 plus 60 squared should be like 3,600. 60 squared. There we go. So we're going to do plus. I wonder if this is a Pythagorean triple. I always do wonder about that. Plus 121. Okay, this is 3721. So to get the modulus, the length, okay, r is equal to the square root 3721. So the square root of the previous, boom. Oh, look at that. It was a Pythagorean triple. Okay. So this was 61. And we should be able to say done. And there we go. Okay. So that's modulus, just finding the length. Okay. Let's see. We're not going to do that. Yeah, we'll let you guys sort that one out. I'm sure I have every confidence that you guys can do that. Write it in polar form. Okay. So remembering that polar form. Okay, this is going to be r times cosine of theta plus I sine of theta. Okay, so that's what we're doing. Okay, let's draw it. So we've got 1, 2, 3, and then 1, 2, 3, 4. We'll call it somewhere around here. Okay, but there is our 3 minus 3 root 3 I. Okay. How do we get the triangle out of? Okay, if I know one side of the triangle is 3, I know the other side is going to be 3 minus root 3I. Okay, here's the lengths. Okay, I would like to know either that angle or this angle. I don't really care which, but that's what I want to know. Okay. So the first thing we have to do is we have to figure out what the modulus is, because that's the r here. Okay. So in order to get that, we're going to say r is equal to the square root of 3 squared plus 3 root 3 squared. Okay. And let me erase that part, because this is just negative root 3 root 3. Okay, the only imaginary part is this part here, not the 3. Okay, so we have r is equal to the square root 9 plus 3 squared is 9. Square root of 3 squared is 3. Okay, so this is 9 plus 27 instead of our square root. This is equal to 36, which is equal to 6. Okay, and now we have to figure out our angles. So this is going to be tangent theta is equal to the tangent inverse, right? So I want this angle, the opposite over adjacent, that's the tangent. So we want to take the inverse tangent of the opposite, negative 3 root 3 over I, or over 3 rather. So the y over the x. So we end up with the inverse tangent of negative root 3. Okay. And if we do that, we know this is going to be negative pi over 3, but we want this in terms of 0 to 2 pi. So we're going to change this around, and we're going to say this is actually 5 pi over 3. Okay, so that's our angle, that's our theta. Okay, so we're going to have r cosine theta plus I sine theta. This is our polar form. Okay, so we have 6 times parentheses, we have cosine of 5 pi over 3 plus I sine of 5 pi over 3. I think that's what they want, so let's go ahead and check. So this is going to be r, well, we're going to be 6 times, we want the cosine of 5 pi over 3, okay, minus, or well, plus, okay, I sine of 5 pi over 3. Okay, and that should be what they're looking for there. All right, yeah. So I'm going to let you guys finish those. Effectively, it's just getting some practice at converting from rectangular form to polar form. So that's pretty much what we're doing with that. Okay. Let's see here. Oh, right, the complex polar form here, 5. Okay, where is 5? 1, 2, 3, 4, 5. How far away from 5 is to the 0, to the origin? The r is 5. What angle is this? Theta is 0. Okay, so this is 5. This is cosine of 0 plus I sine of 0. Okay, and I know it's a little tricky, but that is exactly what they wanted. Okay, this is 5 parentheses cosine 0. Oh, look at that. They don't care about the imaginary part at all. Oh, yes, they will. So plus I sine of 0. Be careful on this one. I know that it looks like, but I could just write it this way. They want it as r times cosine plus I sine theta. Okay, that's what they want. Okay. So even though we all know this is going to be easier, but it's not going to work. Okay. We have negative 10i. Okay, so let's graph this. This is down here, right? It's down here. It's negative 10I. So it's really, the R is equal to 10, but what's my angle here? Angle is equal to 3 pi over 2. So we're going to let this part take care of the negative. We are not touching it. Okay, so the polar form is 10 parentheses cosine of 3 pi over 2. Okay, over 2. Oops, not with dots, I just want, thank you. Plus I sine of, oh, tell you what, let's get rid of this parentheses right here. Plus I sine of 3 pi over 2. Okay, and then we can close this off. That's going to put it in the negative format. Don't put it here. Put it there. Right? And then we're good. Okay, and again, I know, but the cosine is going to be 0. Like, I know, but that's how they want it. Okay, so we're just going to play along with the rules, and it says cosine plus I sine. So even if the cosine term isn't really adding anything, we're just going to put in a cosine of an angle that doesn't add anything. Okay, that's all we're doing. Not going to fight it. Convert to rectangular form. Okay, so now we got to go the other way around. Okay, not too bad. So here we have 12 cosine of 3 pi over 4 plus I sine 3 pi over 4. Which quadrant is 3 pi over 4 in? It's in quadrant 2, right? Because here we go. We have 1 pi over 4, 2 pi over 4, 3 pi over 4. So the cosine is going to be negative, sine will still be positive. Okay? So what is the relevant reference angle for 3 pi over 4 is pi over 4. So what is cosine of pi over 4? So 2 over 2. Okay, plus I, and then we're going to have root 2 over 2. But this is going to be negative, right? Because we're in quadrant 2 here. Okay, so this is going to be 6 root 2, negative 12 over 2 is 6, and then we're just going to leave it. Okay, plus, and then we're going to have 6 root 2, I. And that's my rectangular form there. Okay, so what do we have? We have negative 6 root 2 plus 6 root 2 I. There we go. Okay, so there's a lot of problems. Maybe not a lot of problems. I only go up to 12? Okay. Hold on. Oh, fun stuff. Okay. Beautiful. Oh, we might be able to finish this in one lesson. Okay, let's do that. All right, we have 14. So it doesn't matter about degrees versus radians. Okay, they kind of tell you how they want it here. In general, I'm going to give you a thing where I'm going to say put it in radians, put it in degrees. That's just so that everybody kind of has a checklist of what you're going to do and say, okay, am I done with the problem? Yes, but I don't really take off for that. So try to do your best to say it's radians. If it's asked for radians, do your best to say it's degrees if it asks for degrees, but don't stress over it. Okay, stress over more like, did I get it in the right format? So this is root 14 cosine 360 plus I sine 360. And if you're wondering, like, the angle is always going to be the same? Yes, because we abbreviate it CIS theta. And this means cosine theta plus I sine theta. Okay, so we have to know the x part, the real part. We have to know the imaginary part. We have the same thetas for both of them. Okay, so this is the square root of 14. Okay, cosine of 360 this one, cosine of 360, that is 0. So we end up with root 14. There we go. So we have to do something called the Moff's theorem for a second. All right, so I'm going to pause this for a moment, check something out, and then we'll go through the Moff's theorem. Okay, there we go. So we are looking at something called the Moff's theorem now. Okay, and the Moff's theorem says if we want to multiply two complex numbers together or take a power of a complex number, that there's an easier way to do it. Okay, so the idea is like, what if we wanted to have a z squared? Okay, so this is going to be r cosine theta plus I sine theta, this parentheses here, times r cosine theta plus I sine theta. So we're just taking a complex number times itself. Okay, so this isn't too bad because all you have to do is FOIL them together in rectangular and it's going to give you the same thing. Okay, but here what we're going to do is we're going to multiply them together. So we have r times r, that is going to be r squared. Okay, and then we're going to have to FOIL out our sines and cosines. We have cosine theta times cosine theta, so it's cosine theta times cosine theta. Okay, we have plus n cosine theta, well, we have an I, right? Look at this inner part here. We have I sine theta plus cosine theta. So that is I sine theta times cosine theta. Okay, so that's this part. Okay, when I fold the other way around, I've got the outside ones, right? That's also going to be an I sine theta times cosine theta. Okay, that's the outside parts. Okay, and then the last part is going to be I sine theta times I sine theta, so that's going to be a plus I squared sine theta. Okay, what's I squared? Squared is -1, so let's go ahead and do this. So this is cosine squared theta minus sine squared theta, right? That's these parts, okay, plus I, and I've got a sine theta cosine theta plus a sine theta cosine theta. It's a 2 sine theta cosine theta. Okay, now I'm going to ask you, do you remember your double angle formulas? Do you remember what cosine of 2 theta was? Remember, this was cosine squared theta minus sine squared theta, which you'll look at that. And then the sine of 2 theta was equal to 2 sine theta times cosine theta, which is, look at that. So this is equal to sine, or to r squared. And this little piece here, this turns into a cosine 2 theta, right? Plus I sine 2 theta. Okay, so the z squared equals r squared cosine 2 theta plus I sine 2 theta. What do we do if we have z cubed? Okay, so that's going to be z squared times z. Okay, so that's going to be r squared cosine 2 theta plus I sine 2 theta times r. This is going to be cosine theta plus I sine theta. Okay, so we're going to get our r cubed. Okay, so we're going to have an r cubed here. And then we're going to have cosine times cosine. So it's cosine of 2 theta cosine theta. Okay, and then what are we going to have in the middle here? We're going to have an I. Well, actually, hold on for a second. Let's jump a step here and put all the real stuff together. The last terms, right, that's going to be a minus, isn't it? All right, so instead of plus business, we'll put a minus in here. And then here we have a sine 2 theta sine theta. Okay, do that. Okay, and then we'll say plus I, and then we have a sine 2 theta cosine theta, and then we have the other one. So it's going to be cosine 2 theta plus or times sine theta. Okay. Do you remember? Of course you do. Do you remember the sine of a plus b formula, where this is sine a cosine b plus cosine a sine b? Well, what if my a, right, is 2 theta and my b is 1 theta? So we have sine a cosine b plus cosine a sine b. So this is going to be a plus I, and this is going to be a sine of what's 2 plus 1? It's 3 theta. Okay, and do you remember what the formula for cosine of a plus b is? This was equal to cosine a cosine b minus, right, because the signs change on that one, sine a sine b. And if we have our a is equal to 2 theta and our b is equal to 1 theta, we have cosine 2 theta, cosine theta, cosine 2, cosine a, cosine b, minus sine a, you don't say. So this is cosine of 3 theta plus I sine of 3 theta. And then we have our cubed out in front. Okay, so we have our squared is equal to, or sorry, z squared. Okay, z squared is equal to r squared times cosine 2 theta plus I sine 2 theta. We have our z cubed is equal to r3 cosine 3 theta plus I sine 3 theta. I think there's a pattern here. Okay. Now, if you're taking another class where you have to do mathematical induction, you assume this step. Well, you've verified this step. You assume it for n, and then you prove for n plus 1. The rest of us are going to say, huh, there's a pattern there. I'm telling you as the teacher, as somebody who's done this before, that yes, this pattern holds for any value of n you want to, any natural value of n you want to pick. Okay, so this is going to be z to the n is equal to r to the n. Okay, cosine of n theta plus I sine of n theta. Okay. So if you ever found yourself in a position where you had to like find the 27th power of a complex number, there's an easy way to do it, and this is it. Okay. So speaking of finding yourself in a position where you have to find like the 20th or the 5th power, okay, we're going to have 6 to the 5th. I wonder if they'll let me just do this. They will not. Okay, so this is going, let's write the answer down and then we'll translate it. Okay, so this is going to be 6 to the 5th. I have no idea what that is. Cosine of 5 pi over 30 plus I sine of 5 pi over 30. That's what this power is doing for us. So this is going to be 6 to the 5th power. We have cosine, what is pi? 5 over 30, wait, isn't it pi over 6 plus I sine of pi over 6? Okay, so cosine of pi over 6, that's going to be the square root of 3 over 2, plus I, right, sine of pi over 6 was 1/2. And then, oh, this is not going to be a fun number. 6 raised to the 5th power. Delightful. 7776. Okay. Should we, I guess, divide this thing by 2? So we have 3888 root 3 plus I 3888. And that would be our answer for this problem. Okay, if you took the 6th power, 5th power of this number. Okay. Put this down. Bye-bye. Okay. So this was going to be what? 3888. 3888 times the square root of 3 plus I, and then we just have 3888. Okay. We could write BI. We could write it here. That's fine. Okay. And there we go. So that's pretty much what we're going to use de Moivre's theorem for. There are a couple of other applications for this thing. So if you're able to take roots, they work very similar. So to the 1/3 power to the 1/4 power, it's a very similar idea. I always thought this was kind of a neat theorem because you have fundamental theorem of algebra, right? So we have that says like if you have like an x to the 4th, there's up to 4 zeros. You just can say as a student, you're going to say, wait, great, what are they? The fundamental theorem of algebra says, I don't know. That's not my problem. I just, my job was to tell you that there was up to 4 of them. Some might be the duplicates. That's okay. Some might be repeated. We don't care. But where the rest of them are, don't care. But using de Moivre's theorem, you can get the other ones. Okay, but it requires a fractions in here instead. And since we had meetings about this and they said, don't do this to them because it's a little bit weirder because you have to divide by some stuff and it gets a little hairy. It's not hard, but I also don't want to confuse you. I think this is probably good enough. Okay, so in this case, see, this would be a good problem. This would be an excellent problem because here you have, right, a 2 root 3 minus 2i raised to the 5th power. Now, as fun as doing this would be, one, two, three, four, 5, and foiling all of that out. Okay, already I could hear you even now. Not even in the same room. I could say, oh, this is way too much fun that anybody should ever be allowed to have, right? We're not doing this. Okay, what's our modulus? What's our R? Right, it's the square root of 2 root 3 squared minus, well, plus 2 squared. Okay, so this is 4 square root of 3 squared is times 3 plus 2 squared is 4. Okay, so this is going to be 12 plus 4 is going to be 16, which is 4. Okay. Then what are we going to do with the rest of that? We're going to get the theta is equal to the negative 2 over 2 root 3. So that's negative 1 over root 3. So when I want to, oh, that's inverse tangent, sorry, inverse tangent of this. Okay, so inverse tangent of 1 over root 3, this is 30 degrees. Okay, pi over 6. Did they care about degrees versus? They did not care. Let's push the envelope. Let's see if they wanted 30 degrees. It's not really 30 degrees though, because tangent here is right, is down here. So it's really 330 degrees because that's the reference angle. So let's go 330 degrees and see if it lets us do it. Okay, so R is equal to 4. There's our degrees. Okay. If not, we would use 11 pi over 6, I suppose. Okay. So, yeah, it's going to be, is it in the 4th quadrant? Just check. We have x is positive, y is negative, so it's stuff down here. So yeah, it would be 330 degrees. Okay. So let's go ahead and we are going to say this is 4 cosine of 330 degrees plus I sine of 330 degrees. We are going to raise this to the 5th power. Okay, so 2 is 2 squared, raised to the 5th power, right? Raising a power to a power. So this is 2 to the 10th. Okay, and then we have cosine of 5 times 330 degrees plus I sine of 5 times 330 degrees. Oops. I'll look back on it now. I'm looking, maybe radians would have been easier. Okay. The reason I changed it to a 10, you guys all know your 2 times tables up to whatever, right? Sorry, generation thing. When computers first came on the scene back in the 70s, 80s, they said you had to know all of your powers of 2 because that was going to make you a good computer programmer, and that's how we're going to have to think in the future. Here we are. It's a wasted skill. 5 times 530. So this is equal to. So this is a 1,650 degrees. Okay. Now I don't know how many times, but we could just, I want to know, like 360 into. No, the other way around. I want 1650. 30, 360 rather. I just want to know how many times around the circle we went. Okay, we went around 4 times. So if we subtract off 1,650 minus 4 times 360, right? Where did I get the 4? Right there. Okay, so 4 times 360. If I go ahead and subtract that off, we are ending up with a 210 degrees. Okay, so my answer here is 1,024 cosine of 210 degrees plus I sine of 210 degrees, and we'll call it a day. So that's 1024 cosine. Oh wait, did they really? Oh, they wanted it back in A plus BI. All right, fine. What's cosine of 210 degrees? It's right there, 180 plus 30, right? That's 210. So that's cosine. Effectively, it's cosine of 30 degrees, but in quadrant 3. And effectively, it's 30 degrees, but in quadrant 2-3. What's the cosine of 30 degrees? Okay, it is negative root 3 over 2. Putting a negative because of the quadrant we're in. Plus I, what is the sine of 30 degrees? That is 1/2. Okay, so here we go. We have, this is 10, I shouldn't be, I hear you. 1024 times this stuff. Okay, so 1024 divided by 2, that's 512 root 3 negative plus 512, because that's 1/2 times that, I. Okay, so let's go with this. 512 square root of 3. Okay, that should be negative, shouldn't it? And then minus, okay, 512 I. Yeah, because this should be negative 2. Fingers crossed. Hooray. While this could be a quiz question, I've debated asking it before. I know it's got a lot of moving parts to it, but it is a good question. Okay, so that would be, I think that would be, it would be a medium/hard question to do this because there's a lot to put together. All right, but I would have asked it. Okay, I think the last time I taught this class, I ended up picking a different question from a different section, but this one was on the list. So just want to let you know that is a possibility. Okay, so we'll stop this and we'll pick up the other parts of it another day.